Hello, in hyperbolic plane, the triangles are slim. That means if you take any triangle in hyperbolic plane, each side of the triangle is contained in log 3 neighborhood of union of other two sides. So in general, we'll be exploring this property in a general hyperbolic metric space. So we start with a metric space such that any 2 points can be connected by a geodesic, and if in that metric space all the triangles are delta slim for a pre-chosen non-negative number delta, so then we'll call that metric space to be hyperbolic metric space. Okay, so we'll be describing several definitions of this hyperbolic metric space. So let us begin. Let us first begin with the definition of geodesic in a metric space. So let us take 2 points in a metric space. So XD, it is a metric space. A path alpha defined from this closed interval 0, dxy to x is said to be a geodesic between x and y if alpha of 0 is equal to x, alpha of dxy is equal to y, and distance between alpha s and alpha t is equal to mod of s minus t for all st belonging to this interval 0 dxy. So this is the definition of a geodesic. So for example, if you take upper half plane with hyperbolic metric, so if you take this upper half plane and if I take this path alpha defined from this closed interval 0 to log b by a to h2 by the following way. So alpha of s is equal to 0 a e to the power s. So then distance between this alpha s and alpha t, so this is equal to log a e to the power s by a e to the power t. So here I am taking this s to be greater than t. So this will be equal to s minus t. So as per this definition, alpha is a geodesic. So in our earlier lectures, so we have defined geodesic to be length minimizing path. And if I take the arc length reparameterization of that path, so then that thing will give you to be this definition of the geodesic. Okay. So another example, if I take the Euclidean space, now if I take any straight line, so then that will be again a geodesic. So in order to get this definition of geodesic, you have to just take the arc length reparameterization. So now let me define what you mean by geodesic metric space. A metric space x comma d is said to be a geodesic metric space if every 2 points of x can be connected by a geodesic. So again, examples, if you take the upper half plane with respect to hyperbolic metric, so that is a geodesic metric space. Euclidean plane, it is a geodesic metric space. Okay. So now let me define what you mean by slim triangles. So let us take a non-negative number delta. A triangle. So by triangle here, I mean geodesic triangle. So a geodesic triangle delta xyz is said to be delta slim if each side of this triangle delta xyz is contained in the closed neighborhood of union of other two sides. Yeah. So the picture will be something like this. So this is my geodesic triangle. So each side is contained in delta neighborhood of, sorry, here closed delta neighborhood of union of other two sides. So each side of delta xyz is contained in the closed delta neighborhood of union of other two sides. So if I take the side xy, so this is contained in it's in the neighborhood of, so you take this union xz, the side xz union yz, and take the closed delta neighborhood of this thing. So that is, so if I take any point P in the site, so that is if P belongs to the site xy, so there exist, so then there exist Q belongs to yz union this side exit such that distance between P and Q is less than equals to delta. So Q either lies here or here such that the distance between P and Q is less than equals to delta. And this is true for other sides also. So if I take the side YZ, so this will be contained in this closed neighborhood of union of the other two sides. And if I take the side ZX, so this will be contained in this neighborhood. So this is the meaning of slim triangle. So now let me give you the definition of hyperbolic metric space. So let us take a non-negative number delta. So a geodesic metric space x comma d is said to be delta hyperbolic metric space if all the triangles of this metric space are delta slim. And a geodesic metric space XD is said to be hyperbolic metric space if X is delta hyperbolic metric space for some non-negative number delta. So examples, so first example, so this already you know. So if you take this upper half plane with this hyperbolic metric, so this is a log 3 hyperbolic metric space. So all the triangles are log 3 slim. So next example is if you take any tree. So what do you mean by tree? So a tree is a graph without any circuit. And what is the metric on this tree? So it take edges of the tree to be isometric to the unit interval. So then this will give a metric D on the tree such that distance between V and W is a natural number where PW are distinct vertices of the tree. Okay, so for example, if I take this tree, yeah. So this is my tree, and now if I take 3 points, so I want to prove that this tree, it is a hyperbolic metric space. I need to find some delta. So if I take 3 points x, let us take this point to be y and this to be my z. So now, what is the geodesic connecting all these 3 points? Note that here, so this edges are of length 1. So if I take any 2 points, some here, so the distance between these 2 points, it is just the distance in the unit interval. And now if I take this point P and this point Q, so there exists a unique path which is whose length is minimum joining P and Q. So how to get that path? So go from P to this vertex, then here like this. Yeah. So this is my path joining P and Q. And so what is the distance between this P and Q? So if I take this to be my, let us take this distance from P to this vertex to be L1. And this is of unit length 1. This edge is also of unit length 1. And let us take the distance of this vertex to this Q to be L2. So distance between P and Q in this tree, so this is L1 plus 2 plus L2. So now if I take these 3 points x, y, z, so what will be, first of all, geodesic connecting this x and y. So this will be very simple, this one. Go x to this vertex and then from this vertex to y. And what is the geodesic connecting x, z? So there is a unique geodesic connecting x and z. So this tree, it is a unique geodesic space. So this is my geodesic joining xz. And similarly, we have geodesic joining this z and y. It is something like this pink one. Okay. So let us give a name to this vertex. So this vertex, let us call it to be P. So we have a picture of a tripod, something like this. So this triangle is something like a tripod. So you have this X. So this is my Y. And suppose this is my Z. Yeah, so we have a picture of this tripod. So this, in fact, so it is a triangle XYZ in the tree. So note that, so this side XY is contained in union of the other two sides. So similarly, if I take the side XZ, so it will be contained in YZ union XY. So therefore, so this triangle XYZ is zero slim. Okay. So therefore, so these trees are zero hyperbolic metric spaces. So now let me define. So what do you mean by thin triangles? Okay. So let us first take a triangle. So let delta XYZ be a geodesic triangle in a metric space. So let us draw a picture of this triangle. So first, our goal is to find points on the sides so CX. So we need to find point CX on the side YZ, CY in the side XZ, and CZ on the side XY, such that so distance between XCY is same as distance between XZ. Distance between ZCY is same as distance between ZCX, and distance between YCZ is same as distance between YCX. So in order to define a thin triangle, we need to find these points. Okay, so proposition. So let delta XYZ be a triangle in a metric space XT. So then there exist points CX in the side YZ, CY in the side ZX, and CZ in the side XY, such that distance of X to CY is same as distance between X and CZ, distance between YCX Cx is same as distance between y, cz, and distance between z, cx is same as distance between z, cy. So why such points exist? So what is the proof of this? So let us write. So let A to be equal to, so we need to find these points Cx, Cy, Cz. So this will get with the help of uh, linear algebra. So let us see this thing. So let A equal to distance between x, Cy, B equals to the distance between z, Cy, and let C equal to distance between y, Cx. So we need to find this A, B, C first. Now, so what are the conditions? So, so A plus B is equal to, A plus B is equal to, so this is my A and this is my B. So A plus B is equal to distance between x, z. So this is one equation. And B plus C, so this will be equal to distance between z and y. So this is my C, so this is again B. So B plus C is equal to distance between z and y. And at last, C plus A, so this will be equal to distance between y and x. Okay, so we have this three equations. We can solve with the help of this linear algebra. So what you'll get? So this A will be equal to half of, so A will be equal to this half of this dxz plus dxy minus dyz. Similarly, so we'll get B. So B will be equal to half of distance between xz plus distance between zy minus distance between xy. And C will be equal to half of distance between yz plus distance between xy minus distance between xz. Yeah. So this will imply that, so this Cx, Cy, Cz exists. Now let us take the triangle XYZ again. And now note the following. So this is my triangle XYZ. So we obtained these points CZ, CX, CY, such that distance between XCY is same as distance between XCZ, distance between YCZ is same as distance between YCX, and distance between ZCY is same as the distance between ZCX. So now note that there exist points XT on the geodesic joining XCY and XT prime geodesic joining XCZ, such that this distance between X to XT is same as the distance between X and XT prime. So these two distances are same. And so this XT, it lies in this geodesic joining X and CY, and XT prime lies in this geodesic joining XCZ. So this distance from X to XT, you can take it to be T. So therefore, the distance from X to XT prime, so that will be also T. And T will be less than equals to distance between X and CY, which is again same as distance between XCZ. Similarly, you'll get points in the geodesic joining YCZ and in the geodesic joining YCX. Let us call it to be YS and this to be my YS prime. So the distance between Y and YS is equal to S, is equal to distance between YS prime, and this YS and YS lie in the geodesic joining YCZ, and YS prime lies in the geodesic joining YCX, and S will be less than equals to distance between YCZ. And similarly for this vertex also Z, so you'll get point ZR prime, such that the distance between Z to ZR and distance between Z to ZR prime are same. So these two distances, distance between Z and ZR is same as the distance between Z to ZR prime, and which is equal to R. And R again, it is less than equals to distance between Z to CX. Okay, so now we call this triangle to be delta thin if the following holds. So let us take, so let delta to be a non-negative number. So triangle XYZ is said to be delta thin if for all xt prime ys, ys prime, zr, zr prime. So the distances so this distances, so distance between xt and xt prime, so that will be less than equals to delta. So distance between ys and ys prime, so that will be less than equals to delta. And distance between zr and zr prime, so that will be also less than equals to delta. So if this happens, we call this triangle to be delta thin. Yeah, so in the picture, so this distance between xt and xt prime, so that is less than equals to delta. So this implies that because t is less than equals to distance between x, c, y, so this distance will be less than equals to delta. And so distance between ys and ys prime, so that is less than equals to delta for all s less than equals to distance between y, c, z. So therefore, this distance will be less than equals to delta. And similarly, distance between zr and zr prime, so that is also less than equals to delta. So that will imply the distance between this cy and cx, so that will be also less than equals to delta. Yeah, so that is the meaning of thinness of a triangle. So now observe the following. So if a triangle delta xyz is delta thin, so this will imply that delta xyz is delta slim. So this follows from the definition, so the proof is very easy. So you assume that this triangle delta xyz is delta thin. So this is my triangle. So you can split the triangle in the following way. So here you'll get point cx, cy, cz. So this distance between x, cy is same as the distance between x, cz. And distance between y, cz is same as the distance between y, cx. And distance between z, cy is same as the distance between zcx. And now given any point xt here and xt prime here, so this distance, you know that this is less than equals to delta. That is the definition of thinness. And now you want to prove that the triangle is delta slim. So let us take some point. So let P belongs to xy. So xy means here the geodesic joining xy. So this will be equal to the union of these two geodesics. So this means that P either belongs to this geodesic joining xz, or P belongs to the geodesics joining czy. And now suppose P belongs to this, P belongs to the geodesic joining xz. Suppose P is here. So then obviously you'll get a point in the geodesic joining xcy. So you'll get a point Q on the geodesic joining xcy such that the distance between P and Q is less than equals to delta. So this will imply there exists Q in xcy such that distance between PQ is less than equals to delta. And suppose P lies in the geodesic joining CZ, CY. Suppose P is here, again you will get a point here Q, such that the distance of Y to P is same as the distance of Y to Q, and this distance is less than equals to delta. So this follows from the thinness. So there exists Q belongs to this geodesic such that distance between PQ is less than equals to delta. Okay. So this part is easy. So if a triangle is delta thin, so it will be also delta slim. Now let us move to another proposition. So this is also very important. So let delta greater than equals to 0. Let XD be a geodesic metric space such that all the geodesic triangles are delta slim, then there exists a delta 1. So this delta 1 depends on delta. So there exists a non-negative number delta 1 such that all the triangles are delta 1 thin. Yeah, so here you have to assume that all the triangles are delta slim. So then you'll get some non-negative number delta 1 such that the triangles are delta 1 thin. Okay, so let us see the proof of this. So let delta XYZ be a geodesic triangle. And we know that from the hypothesis, so delta XYZ is delta slim. So this triangle is delta slim. Okay, so now let us take this triangle. So again, you can split this triangle as earlier we have done. So you'll get this point CZ, CY, CX. So the distance between XCY is same as the distance between XCZ. Distance between YCZ is same as the distance between YCX. And distance between ZCY is same as the distance between ZCX. Okay, so we have assumed that this triangle is delta slim. Now for this point CZ, so I'll get a point CZ prime either on XZ or YZ such that the distance between CZ and CZ prime is less than equals to delta. So let me write down this thing. So there exists CZ prime XZ union this geodesic YZ such that the distance between Cz and Cz prime. So that is less than equals to delta. So let us assume Cz prime, it belongs to Xz. Okay. So again, note that so this Cz prime, it may lie either in the geodesic between XCY or in the geodesic between CYZ. So X, this geodesic XZ. So this is the just the union of these two geodesics, X CY union this geodesic. So this implies that CZ prime, it lies in this union of these two geodesics. Let this CZ prime, it belongs to XCY. Yeah. So the CZ prime, it belongs to this XCY. And we know that this distance is less than equals to delta. So now, so this distance between Cz prime Cy, so this will be equal to distance between xcy minus distance xcz prime. So distance between xcz prime is equal to distance between xcy minus, sorry, so the distance between cz prime cy is equal to distance between xcy minus distance between xcz prime. So that thing we have written here. And again, so distance between xcy is same as the distance between xcz. So we have this equality here. And now apply the triangle inequality. So distance between xcz is same is less than equals to distance between xcz prime plus distance between cz prime and cz minus distance between xcz prime. So this two terms, distance between xcz prime and here the distance between xcz prime, so this will cancel. And distance between cz and cz prime is less than equals to delta. That comes from the slimness. So therefore, distance between cz prime and cy is less than equals to delta. Now by triangle inequality, so distance between cy and cz, so that will be less than equals to distance between cy cz prime plus distance between cz prime and cz. So that will be less than equals to twice delta. Similarly, if I get this cz prime on this geodesic, so then also you can prove that distance between cy and cz, so that will be less than equals to twice of delta. So this I will leave as an exercise. Okay, so what we have proved that if the cz prime, if it lies on the site xz, so distance between cy and cz is less than equals to twice of delta. And similarly, if cz prime if it lies on the geodesic joining y and z, So you can prove that the distance between Cz and Cx, it is less than equals to twice of delta. And now if I take this point, so let us take this point. So let us take the point Cx. So then there exists Cx prime either in the geodesic joining xz or on the geodesic joining xy, such that distance between Cx and Cx prime is less than equals to delta. So depending upon the Cx prime, so what we'll get, so this will imply, so either distance between Cx Cy is less than equals to twice delta, or distance between Cx Cz will be less than equals to twice of delta. So this will imply that, that diameter of the set Cx, Cy, Cz, so this is less than equals to 4 delta. Okay, so let me recall what we have done. So we have started with this triangle XYZ, and we got these points CZ, CX, CY. So this distances are same, and the diameter of the set Cx, Cy, Cz, so that is less than equals to 4 delta. So that we got. Now what we are going to show, so if I take this point xt and another point xt prime, on the xt prime lies on the geodesic joining x and cy, such that the distance of xt prime, xxt prime to distance between xxt are same. So these two distances are same. So we are going to prove that this distance is bounded in terms of delta. So if you can do that thing, then we are done. So for the other part also, we'll do the same kind of thing. So we'll take here yt prime, and we'll show that this. So if we show that the distance between xt and xt prime is bounded in terms of delta, so then the same proof will work for this part also. Okay, so now let us take this triangle x, cz, cy. And now let us take these 2 points, xt and xt prime, such that the distance of x to xt is same as the distance of x to xt prime. Let us take it to be t, where this t is less than equals to distance between xcy, which is same as the distance between xcz. Again, we know that this triangle x, cy, cz is delta slim. So this means that the distance of xt to CZ CY union the geodesic X CY. So that will be less than equals to delta. So this implies there exists a point P in the geodesic joining CZCY or P in this geodesic such that the distance between xt to P is less than equals to delta. Okay, so now suppose first this so this P, it belongs to CZCY. So then, so already we know that this distance, so this distance is less than equals to 4 delta. So therefore, the distance of, so then the distance between this xt and cy, so this will be less than equals to 5 delta. Now suppose, so this P, it belongs to the geodesic joining xcy. So then this P, it belongs to either this geodesic joining xt prime or P belongs to this geodesic joining xt prime and cy. So that is clear from this picture. Now suppose this P, it belongs to the geodesic joining xt prime and cy. So then, so this distance between P xt prime, so that will be equal to distance between xp minus distance between xt prime. So distance between xp is less than equals to distance between xt plus distance between xtp minus distance between xt prime. Now because this distance between xt is same as the distance between xt prime, so these two terms will cancel. And distance between xt and P is less than equals to delta. So that will imply that distance between P xt prime is less than equals to delta. So this will imply that the distance between xt and xt prime by triangle inequality is less than equals to 2 delta. And we are done. Similarly, if I take this P on this geodesic, so this will also imply that distance between xt and xt prime, so that is less than equals to twice of delta. So now if I take, so let delta 1 equals to, let us take it to be 6 delta. So then what we have proved that, so this triangle XYZ is delta 1 thin. So we have proved the proposition. And now let me end this lecture with this comment. So in the definition of hyperbolic metric space, so X is delta hyperbolic metric space if triangles are delta slim, or also we can take triangles are delta thin. So if I take all the triangles to be delta thin, so then this space X is said to be delta hyperbolic metric space. And if we take all the triangles to be delta slim, so then that will also imply this X to be delta hyperbolic metric space. Okay, I'll stop here.